everyone, this is the first experiment weighing with different balances and the mole concept. So in this video you're going to learn the basics, understand it, and know how to apply it to solving some other problems. Now, a mole is the amount of substance that contains as many elementary particles, which could be an atom, molecule, or ion, as there are in exactly 12 grams of carbon-12, which is equal to the Avogadro's number. Someone might ask, why carbon-12? Now, carbon is specially chosen due to its elementary particles. It has exactly 6 neutrons, 6 protons, and 6 electrons. So, and 12 grams of carbon-12, finding the number of moles of 12 grams of carbon-12 will give you exactly 1 mole. So, 1 mole is the amount of substance that contains those elementary particles, which could be an atom, molecules, or an ion. Now, this implies that 1 mole of any substance contains the Avogadro's number. 1 mole of a book contains the Avogadro's number. 1 mole of sodium contains the Avogadro's number. 1 mole of chemistry, as we are dealing with in this particular context, contains the Avogadro's number. Now, this is an illustration between mass, mole, and volume. This is very important. It could help you be able to know how to convert by using the right formula. So we have the first one here. As you can see here, this is the lower arrow. You can see from moles to mass. Okay, what are you going to do for you to determine the number of moles? If you're given the number of moles, you want to convert it to mass, all you have to do, the small letter n is called number of moles, the capital letter M is called the molar mass, that is mass of 1 mole. So always multiply the number of moles you are given by the molar mass in order to convert it to the mass in grams. That is what this means. So now if you're converting from the mass, if you're given a mass and you're asked to calculate the number of moles, okay, all you have to do is, you can see the relationship at the top, small m divided by capital letter M. The small m means the given mass, which you want to convert to get you to the number of moles, divided by the molar mass of that substance. That will automatically get you to the number of moles of that substance. So given mass divided by molar mass is number of moles, but number of moles multiplied by the molar mass will give you the given mass from this illustration you can see here. Now, if you want to convert a given number of moles to volume, as you can see here, the downward arrow, you can see small letter n multiplied by capital letter V. All you have to do is multiply the number of moles you're given with the V. The capital letter V is the molar volume of any gas, which is a constant, a standard temperature and pressure, which is equivalent to 22.4 dm cube. So if you're given the number of moles, you want to convert it to the volume, all you have to do is multiply by 22.4 dm cube. And that is why you can see over here, there's an illustration for the key, which will help you understand it better. So M is the given mass, capital letter M is the molar mass, the small v is the given volume, and the capital V is the molar volume. Okay, now let's go back to this again. So if you're given a volume and you want to convert it to the number of moles, so all you have to do is divide the given volume by the molar volume. That automatically converts the volume to the number of moles. You can see if you're converting from the number of moles to the number of particles, you can see the downward arrow here. So converting from number of moles to particles, all you have to do is multiply it by the Avogadro's constant. So you have a value already in moles. You want to determine the number of particles in that substance. So if, for example, 0.1 mole, you want to convert it to particles, automatically multiply by 0.02 times 10 to the power 23. Whatever value it gives you is the number of particles for that particular substance at that 0.1 at that particular specific number of moles. Now, if you're converting from number of particles to the number of moles, you can see here the upward arrow. You can see this upward arrow. Converting from the number of particles to moles, all you have to do is whatever value the number of particles is divided by the number of moles for that substance multiplied by 6.02 times 10 to the power 23. That is the Avogadro's constant. So with this relationship, you should be able to convert between mass, moles, volume, and number of particles. This is very important. And don't forget to refer to the key to understand this concept. Let's go to the next slide. Now, this is an example how to calculate the amount in moles. So, we have a problem here. Determine the number of moles in 95 grams of manganese 4 oxide. You are given the atomic masses to be 54 for manganese and oxygen is 16. Now, how do you determine the number of moles? Don't forget, number of moles is equal to given mass over molar mass. Number of moles is equal to given mass over molar mass, as you can see here. So, that is to say, looking at this, you want to get a given mass to number of moles. Alright, all you have to do is divide the given mass divided by the molar mass, as we've illustrated earlier. So now, what do we have here? We have a given mass of 95 grams, okay? And this information is going to help you to calculate the mass of given mass 95 grams divided by what is the summation of the individual atoms in this substance, manganese 4 oxide. All you have to do is manganese is 54, okay, plus oxygen. We have 2 atoms of oxygen, so 2 open bracket multiplied by 16. So that will be 54 plus 32. So whichever value it gives you is the molar mass. So that is what we've done here. As given mass, which is 95, divided by the molar mass. So whatever value it gives you is the number of moles for the 95 grams of manganese 4 oxide. Now, how do you calculate amount in grams? As illustrated earlier from the first slide, amount in grams is number of moles multiplied by the mass of 1 mole, that is the molar mass. Now, take a look at this. You are given the number of moles, 0.52, okay? And you are also given the individual atomic masses, which will give you an insight to the molar mass, which is the mass of 1 mole. So to determine the amount in grams will be number of moles times the molar mass. That will be 0.52. As you can see here, 0.52 multiplied by 86, which is the molar mass of, or mass of 1 mole of the manganese 4 oxide. And you know this particular information. So this is what you basically need to know. Here again, you're expected to know the difference between precision and accuracy of weighing apparatus. Now, in chemistry, accuracy is a measure of how close a measurement is to the actual value. Precision is a measure of how close a series of measurements are to one another. Now, I'll be making an illustration with this, the bullseye and a dart. Now, from this first illustration, you can see here, there are 3 arrows pointing directly to the bullseye. These 3 arrows, you can take them to be a series of measurements. Now the bullseye is the actual value, that is the target. So as you can see here, these 3 values, these 3 arrows are pointing directly into the bullseye, meaning that there is a high accuracy and very much good precision because these arrows are clustered. They are so close together. So how close a series of measurements, how close these arrows are to each other implies how precise they are. So if values 4.5, 4.6, 4.7 are considered as measurements, they are said to be precise. Okay, now precision has nothing to do with the actual value, but accuracy has a lot to do with the actual value. You make reference of accuracy to an actual value, but you make reference of a series of measurements to one another in the case of precision. Now look at the second one. You can see here, this is the target, the actual value, and you can see these values are more precise. These arrows are very precise in the sense that they are very close to each other, but they are far away from the target, meaning there is high precision but low accuracy. Poor accuracy, good precision. Now the third one you can see here, look at the arrows, very much apart. The measurements, the values are very much apart, and they are not even close to the actual value that is the target. Here you can say that there is poor accuracy and poor precision because the values are far apart. The arrows are far apart and not even close to even the target. So there's a poor accuracy and poor precision. Now we'll be looking into the accuracies of two measuring or two weighing apparatus. One is the top loader. This is what the top loader looks like. Now the top loader weighs to an accuracy minus 1 milligram, that's equivalent to 0.001 gram. They are suitable for most weighings of amounts that are specific or specified to only 2 or 3 significant figures readability. So when accuracy is not of paramount interest, you are advised to use the top loader, and especially when you're interested in results that are rounded to 2 or 3 significant figures. Now the analytical balance weighs to an accuracy of plus or minus 0.1 milligram, which is plus or minus 0.0001 gram. They can be used whenever you desire 4 or more significant figure readability accuracy, and if extreme accuracy is not important, a top loading balance will work just fine in measuring the accuracy. So the analytic balance is most accurate and mostly employed where accuracy is paramount. If, for example, you are asked to weigh out about 2 grams of a certain substance, it actually means that you are required to weigh an amount of approximately 2 grams. And it also implies that the accuracy to which this amount needed is not actually high. Therefore, you need a top loader to actually do the weighing. But if you are asked to accurately weigh out, the word there is accurately, weigh out 0.2 gram of a certain substance, it means that you should, with the aid of an analytical balance, weigh out an amount that is close to that particular value. And it does not mean that you must necessarily weigh out exactly that value, but an amount close to 0.19 or about 0.21 is perfectly acceptable.